Now we continue with network databases. So network databases represent an evolution from hierarchical databases we discussed last time because they address some of the limitations of the strict tree structures. So while hierarchical databases see data as a tree of records, with each record having one parent and many children, network databases allow each record to have multiple parent and child records, forming a generalized graph structure. This flexibility makes network databases much more suitable for complex business relationships. In risk management, for example, a customer might have relationships with multiple products, multiple branches, and multiple risk categories simultaneously, something that's difficult to represent in a strict hierarchy. A network database allows multiple member records or files to be linked to multiple owner files and vice versa. This many-to-many relationship capability makes the data model much more realistic for complex business scenarios. The relationships in network databases form a net-like structure where a single element can point to multiple data elements and can itself be pointed to by multiple data elements. This creates a web of interconnected relationships that can more accurately represent real-world business complexity. For example, in a risk management context, you might have customers connected to multiple loan products, each loan product connected to multiple risk factors, and each risk factor connected to multiple regulatory requirements. This complex web of relationships is much easier to represent in a network database than in a hierarchical one. Modern examples of network-like databases include graph databases, such as Neo4j, which are particularly useful for fraud detection and social network analysis, and for understanding complex relationships in financial networks. XML databases like eExist also incorporate network-like features while maintaining hierarchical organization. Now here you can see a visual example of network database structures, illustrating how the flexibility of network models allows for more complex and realistic data relationships compared to strict hierarchical structures. So the diagrams represents how entities can be interconnected in multiple ways, forming networks rather than simple trees. In the left diagram, you can see how different entities like customer, product, order, and shipment can have multiple interconnections, representing the complex relationships that exist in real business scenarios. The right diagram shows a more complex network where entities like store, customer, manager, and salesman, and items are all interconnected. Notice how, unlike a tree structure, entities can have multiple connections going in different directions. This type of structure is particularly relevant for modern applications like fraud detection, where you need to analyze networks of relationship between customers, account transactions, and merchants. Graph databases like Neo4j, which are mentioned as examples, excel at this type of analysis. In the network model abilities to represent complex many-to-many relationships makes it very valuable for AI applications that need to consider the broader context and relationships within data, not just individual data points in isolation. Next type is relational databases. Now, relational databases, which became dominant in the 1980s and remain the foundation of most business applications today, represent a significant advancement in data organization and management. In relational databases, items are organized as a set of tables with columns and rows. Now, this might sound simple, but this tabular structure, combined with mathematical principles of relational algebra, provides the most efficient and flexible way to access structured information. Think of each table as representing a specific entity or concept. In risk management, you might have a customers table, a loans table, an accounts table, and a transactions table. Each row in a table represents a specific instance: one customer, one loan, one account, or one transaction. Each column represents an attribute or property of that entity. What makes relational databases powerful is the ability to establish relationships between tables through common fields, which typically we call them keys. For example, both the customer tables and the loans table might have a customer ID column, which allows you to connect customer information with their loan details. Relational databases are normalized, meaning the data is organized to reduce redundancy and improve data integrity. So instead of storing customer name and address information in every transaction record, you store it once in the customers table, and then you can reference it using the customer ID field. This normalization is particularly important for operational data, the day-to-day transaction processing that keeps businesses running. SQL databases excel at handling these operational workloads efficiently while maintaining data consistency and integrity. Now, the combination of structured organization, mathematical foundations, and powerful query capabilities makes relational databases ideal for the reliable, consistent data management that AI and risk management applications require. Next, distributed databases, which represents an important development in database technology to address the needs of large organizations that operate across multiple locations or need to manage massive amounts of data that exceeds the capacity of a single system. So a distributed database consists of two or more files located in different sites. This doesn't just mean different folders on the same computer. We're talking about databases that span multiple computers, potentially in different cities or even different countries. The database may be stored on multiple computers located in the same physical location. For example, multiple servers in the same data center working together to handle large volumes of data or provide high availability through redundancy. Alternatively, the database components can be scattered over different networks, such as having customer data stored in the regional data centers to comply with local privacy regulations, while still allowing global access to authorized users. Distributed databases are particularly important in today's global business environment and are essential for many AI and risk management applications. For instance, a multinational bank might need to store customer data in the country where the customer resides, while still allowing risk analysts at headquarters to access aggregated anonymized data for portfolio analysis. The challenges of distributed databases include ensuring data consistency across locations, managing network latency, handling failure, and maintaining security across multiple sites. However, the benefits include improved performance, enhanced availability, and regulatory compliance, which often makes distributed architectures necessary for large-scale AI and risk management systems. Modern Cloud computing platforms have made distributed databases more accessible, with services that handle much of the complexity automatically, while providing the scale and global reach that modern businesses require.